Alright, let me just explain something to you. Our magnetic North Pole is shifting extremely fast. This is called Geomagnetic Reversal. When this happens, the whole planet flips. The North Pole goes to the South Pole goes to the North. I don't know what the ramifications are, but I suspect they would not be good. Now, they say that they estimate this happens on an average of every 7,000 years. Now, on the Sun, it happens every 11 years. And at 11 years, it charges, and then on 27 days, it flips. So we could flip. We may be in the midst of flipping now. If it takes 11 years for the Sun to charge up, and then only 27 days for it to completely reverse its magnetic fields, and that's the case. If we charge for 7,000 years, how long would it take us to reverse our magnetic field? It might take 100 years. It's just a process of moving forward through that process of reversal of fields, and I think we're in the midst of it right now. That's all I can take away from this, because I'm seeing that we have devastating effects on the Earth, and these tornadoes and floods and hurricanes and violent interactions in the upper atmosphere are causing this. Okay, my friends, this is the most important video I've ever done. Have you ever seen anything that glowed that did not give off heat? Have you ever seen anything? They used to take fire to sticks and rub them together so many hard until they would actually burst into flames. But then they would start to glow. Why would they start to glow? By rubbing sticks together. Why does the sun glow? Why is the earth overheated? They're talking about CO2. This is not the way to go. I'm going to show you why. Okay, we're going to just cut right to the chase. This is red laser light. It's supposed to go only one speed. Obviously, no question in my mind, I don't know about yours, that is accelerating. And what is accelerating? There's a beam shooting right out of it. Well, what is that beam? That beam is this particle. And what is that particle? It's light. Light is a particle. That is a particle. Not only is it a particle, when it hits something, it slams it like hell and turns extremely bright. What does that mean? That's energy. That's heat. That is literally extreme amounts of heat right in that one spot. Have you ever seen anything that glowed that did not give off any heat? Think about it. So as you can see, the light came out, the light accelerated, the light is a particle. Now, I am going to show you extreme resolution of that particle, and then we're going to determine why it glows. Before we go to that shot, remember this shot right here. The wave is coming through. The particle is way back in here, but it has a magnetic field in front that pushes every other magnetic particle, which every particle there is magnetic. So everyone glows as they have to get out of the way. That's the only reason we're seeing all these little dots of light. Now, let's look at the extreme version. Alright, this is extremely resolved. That is the radiance, it's the luminosity of a photon. You're not looking at the particle itself, you're looking at its luminosity. This is what is the luminosity, is the white particle. The black particles don't change. Those are the muons. And I believe they are dark matter, and they also account for gravity. They pull back the white particles. Now remember I showed you those little particles in the air glowing? That's them right there. Because this particle has to push them out of the way. It's coming through. This one doesn't glow because it has its dark matter preceding it. So it doesn't get hit by the particles. These hit the glowy electron and charge it up. And as it charges up, eventually it'll reach enough resistance, it'll flip. Then this one will come in front and charge up, and then it'll flip, and that's what's called up and down spin. Now, this is what they're now referring to as a tetraquark, which is the four particles. Cornell called them 2p, 2h, which is two particles, two holes. Now they're calling them tetraquarks. They have all kinds of names for them, but they don't know how to do it like we do. They're trying to do this and observe these from gigantic explosions with protons. We use photons. We use light right from the beginning, so we know exactly what we got. They have no clue what they are. Okay, I think I've just shown you that light appears to be a particle, and it is a magnetic particle. And we know that when that magnetic particle hits something, it bounces back and radiates back as what we see as light. So coming out of the sun. This is a lunar eclipse. I mean a solar eclipse. The moon is in front of the sun. So we are seeing the radiation of the sun. You see the pole? There's the pole right here. You see that? That's the equator. That's where it's spinning and rubbing much harder than the poles. The poles literally are magnetic flux flowing through here because this is literally scrubbing through all of the electrons that are in space. Identical, absolutely identical to an electric DC motor. All right, we know the sun is spinning. We know the earth is spinning as we drift through space. Well, has anybody really thought about that critically? I have. I understand why we're spinning. And if we stop spinning, we would start spinning again, and I can tell you exactly why. All right, let's just think about this. This is a galaxy, it's spinning. Let's just say it's the Milky Way. Whoops. It's spinning in a circle like this. That means the arms are bending back because they're crushing into all of the atmosphere that's out here, which is those particles of light. So let's start with that. Here we are in a galaxy. So we are here. We're being scrubbed forward through whatever's in front of us. We have to scrub through it. Anytime you scrub through something, you create heat. All right, just think about this. Here we are on the arm of the Milky Way. We're being scrubbed through everything that's in front of us. Additionally, we're all spinning on our own axes, and we're also rotating around the sun. The sun is just plowing through everything and being stripped of its particles, and we have to plow through those. That's why during the daytime, when we're facing the sun, we are just being illuminated with all of its particles, and it's literal dust. We're concussing. That's why it's hot. During the day, the light filters right down onto us. Now, if we put a dome around the Earth with the particles, yes, we wouldn't feel so hot down here, but it would get hotter than hell up there, and it would destroy our atmosphere eventually, totally. Our only chance to survive this is to stop expanding the atmosphere, our envelope of atmosphere. Because I will show you how we scrub. And we scrub with that ionosphere against all the particles that are in space. And that's why John Glenn saw the particles glowing. Anytime you see something glow, it means it's giving off heat. Okay, so now we know that we're spinning through all the particles that are in front of us. And what would that look like here on Earth? Well, it would look like this. These are all particles. They're all particles. Remember I said when you push against another particle, it glows? These are particles out here too. We're spinning very, very fast through that, crushing through all those particles. That's why it's 2,700 degrees out here. You might not have known that. It's 2,700 degrees out in our ionosphere area, out in the end of our atmosphere, where it scrubs into space. And it is charged like crazy. That's why we get 50 lightning bolts a second on Earth, because we're flushing electrons into this atmosphere. And it just charges up our system. Now, if this envelope of gases, and that's all it is gases from here out. There's all the different gases. And the more we burn things, the more gases we put in our atmosphere. That makes our atmosphere get out here closer and closer out, to crush harder and harder. Now we're a bigger ball. That's what the whole thing is with combustion. Carbon dioxide has nothing to do with it, really. Carbon dioxide creates a lot of polar molecules, yes. But it's not, the reason is the scrub. It's the scrub. If they put more particles out there, you're going to have more scrub. I don't know how they can think that's going to stop it. We may be able to put a shield around there, like an umbrella, but it's when they hit, they are not going to go away. They don't bleed off into space. Some do, but it's just not a passive system that comes and goes and everything's fine. No, this has been a charging system forever, and it will charge and charge and charge. And what will end up happening is it will reverse. It will flip, just the way the sun did. And the sun does it every 11 years. It's a polar shift. Now, I don't know what would happen on Earth. This one's charging like crazy. Well, you can see it. You can see how much it's charging. We're not getting charged up as much, but we are getting pretty heavily charged now. The polar shift is very fast, which means, just as I showed you, well, I'm going to show you again. Okay, just think about this. It says a new study suggests there may be another way to make oxygen from carbon dioxide. So what is carbon dioxide? It's a carbon molecule and two oxygens. All right, they bond together. Well, guess what? Ultraviolet light can split them apart. So you can get your oxygen and your carbon apart. Well, guess what the sun puts out? It's a ton of ultraviolet light. So how could carbon dioxide in the outer atmosphere be the problem? It would just be making more oxygen, it looks like to me. So what is the true nature of our outer atmosphere? Well, the carbon gets stripped off and you end up with oxygen and hydrogen, and which is a extremely polar negative molecule that has a ton of resistance to scrub against other negative particles which are out here. And all sunlight is particles that are they're polar, they're magnetic. And what all a motor is you spin these little magnetic particles through a magnetic field, and that creates, you pulse it, and it drives the motor forward. And that's all we're doing, only we're just scrubbing like a tire against the pavement with the brakes on. And that's what heats this up out here. 2,700 degrees, exactly identical to the sun. Do you know that the sun's surface is only 7,000 degrees? And where it is way out here at the corona, just like us, where it scrubs, it's millions of degrees. They have no way to account for this, none whatsoever. They say, oh, it's fusion. I say, well, how does the fusion work? Well, the fusion's crushes it all up and it makes it fuse. Well, why does it get hot out here and only 7,000 degrees here? That doesn't make any sense. Well, you just don't understand. I said, that's right, I don't, because it doesn't make any sense. Same thing with what they're talking about with this atmosphere. Same thing they're talking about the vacuum of space. Where do you think these things go? I showed you the solar eclipse. You can see they're everywhere. We know we're scrubbing through them. They're called everything, the solar wind. I mean, light is a particle. I showed you that. If they discount us scrubbing through that and just, that means nothing to anybody, we're just lost, literally lost in space. No, I thought I had the sound off, but I don't. Anyway, they're showing where it was in 1840, and now it's way over here. And look how fast it drifted from 2000 to here. This is just within the last couple of days. You go back 150 years or whatever it was. It took that long to get there. Now, in 20 years or so, we're already there. And it is moving very, very fast. Look, at 2019, it's way over here. That's just more distance than it was in that whole other time. All right, that's just telling you the location drifting from 1840, so we've got 1900, that's 60 years, 2000 is 160 years. And you saw that it drifted in the last 20 years more than it drifted in the other previous 160 years. That is not good. All right, this is one of the most sacred laws of physics. Nothing can travel faster than the speed of light in a vacuum. Well, what is a vacuum? A vacuum means there's no particles in there. There's no particles to restrict the light, to slow it down. So it travels at a consistent speed. Nothing interferes with its forward motion. All right? But if something was there to interfere with its forward motion, it would slow it down. It would not accelerate it. So nothing can accelerate faster. You can slow them down. We know they can slow them down. So nothing can ever travel faster than the speed of light in a vacuum. But this speed limit has been smashed in recent experiments. A laser pulse travels 300 times the speed of light. And then they say, oh, we can figure this out because this is wave dynamics, wave propagation. Well, how do you propagate a wave in a vacuum? Where does a wave go? It's just, how does that wave move? What is it? Just, it's a wave and it just goes by itself and there's nothing in front of it? That's possible. But how could you speed it up? Well, here's how we sped it up. Okay, here's how we sped up light. And we didn't use a vacuum. So we have all kinds of particles in the air in front of this wave of light. Well, guess what? That should restrict it from flowing faster, but no. We accelerated it through that field of particles. We don't care about a vacuum. We can accelerate even in this resistance. And that is the particle being accelerated. And the reason is because we made a venturi there. It was exactly the correct dimensions to allow only the white to come through. We got lucky using the pulse laser, and this exact specific design created cold fusion. This is the holy grail. I need somebody to talk to me. This is where the particles divided. Here's where they came back. That's fission, that's fusion. This is cold. We didn't add any additional energy here. This is the particle, right? It's two particles and two holes, they call it, 2p, 2h. Now they're calling them tetraquarks. It's nothing more than a photon. And a photon is nothing more than two electrons. But each electron is composed of a glowy part and a black part. So they're bar magnets. Basically, that's all they are, is tiny little bar magnets. They have an atomic weight. They weigh 0.0005585, something like that, atomic mass units. 1,839 of electrons. Divide 1,839 into 1, and that's how much they weigh. Because one atomic mass unit is a proton. 1,839 of these, electrons, and this is 2 electrons. 1,839 electrons make one proton. 1,840 make a neutron because they become neutral. They don't have an extra electron laying around. Now, we accelerated light. We can see the particles, that light is a particle. There's a very little question about that. Very little question that we accelerated. Very little question that we were not in a vacuum, so it should not accelerate by any means whatsoever, but it did. And what did it do when it accelerated? It did exactly what CERN wanted. It exploded and gave us fission, and then gave us fusion. And this is raw energy, and that raw energy should be 207 times the input value. That's CERN's and Fermilab's words, not mine. These are those little black balls. They don't care about touching each other. The whites hate each other. And that's why you had this interference pattern. The interference pattern is not from flappy waves. This is a single slit. We need a lot of work on this physics. And they need to contact me, because I have the information. Rod Warren and I have done this for many years now. And it's been totally rejected, and it's very upsetting at this point, because they keep saying, oh, we're looking for answers, we got to do something, we got to do something. Not a single one of them will respond to me. And not a single one of them will debate me, because they know I have the answers right in my hand here. And for their ego to keep them away from helping the world is just, it's I don't want to say nasty things about people, but it's kind of disgraceful, really. If they won't talk to me, and I can do this for almost nothing. I mean, literally free almost. And we can change the world literally overnight, because all of this stuff exists right now. You can see it's being done. And if all we have, put a harvester right here, and I have the design to do it, but somewhere around here. Basically all it is this. You have the laser pulsed, bip, 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 bip. Let's say it's a 5 watt. It goes through the venturi, nothing added, it splits. Here we have 1,000 watts worth of energy, 200 times. And we can harvest it here. And then run it through our devices, take a little extra, keep the laser running. We got free energy, solid state, nothing to do, nothing to add, nothing to worry about. Carry them around in the woods, anywhere you want. In a little box, handheld. You get a ton of power out of a little tiny laser. That's what I'm suspecting. Now, they spend billions and trillions of dollars experimenting in all these different things, and will refuse to engage with me for something that less than $100 you could make somebody power their house, power a car, probably power an airplane for a couple $100. It's this simple. Alright, I think I've made my case. This is where I can get contacted, roger@mudfossils.com. This is raw energy as far as I'm concerned. If we can harvest this and slow down the expansion of gases from non-combustion, because this is not dangerous in any way whatsoever. We're working with light. You get hit by light all the time. You don't want to be right there. But you can. This is only like a bazillionth of an inch. This is not a big distance away. So you're just going to have it in this little box, and it's going to do what it does and pump electricity out. The electricity won't hurt you. The electricity runs all the devices, and then it will find its way back to the dark matter. We have to just filter it through our devices and come back to the dark matter to become whole again. And in the meantime, it increases its energetic value 207 times here. So if we put 5 watts in and had 1,000 watts out here, right? 200 times 5 is 1,000. Right? So we started with 5, we get 1,000. That's a hell of a lot of extra energy. We, of course, use, let's say, even half of it to keep our devices going. We still got 50% free energy. You never have to do a thing. The laser just keeps pumping. All you got to do is keep feeding electricity into it, and that's what we're going to get out of here, because we have divided the particles. We have cold fission. All right, we divided these with not any extra energy whatsoever. They're using megajoules, billions, and I mean, absolute unbelievable amount of energy, and they never get even close to what they put in back. We put in 5 watts. Look at what we're getting back. We didn't add anything at all here. I think I deserve an audience with this, because it's been years, and they keep saying they're looking for answers, and I have not had one person allow me to speak. And I mean allow me, not you know, they won't debate, they won't discuss. I've been blocked. I've been denied access to every single place that has speaking about this. Fermi Lab and NASA and everywhere, 100%. If my posts are going up there, I don't think they are. Well, I know they're not working with me at Fermi Lab. I can guarantee you that, because that's already down the tube. You know, I tried, and they just said, no, you're not peer reviewed. We're not going to look at your stuff. So what am I going to do? Nobody. And I said, well, you peer review me? No, because you're not peer reviewed. Well, I would like to save the planet and have somebody take an interest for reality, not just to play a game for status and ego and so forth. This is just something that needs to be done to try to save our kids' future. And I'm going to tell you what, I got to be honest with you, I don't think it's doable, but it's certainly worth a try, because there's nothing else they're going to do that I can see they're thinking about that has any possibility whatsoever of working, because they don't even know what the space is filled with. It's filled with all of these particles. Okay, as I showed you before, this is the light accelerating. Now this is extremely magnified. Now this is an upspin, where the North Pole is at the top. This is a downspin, where the North Pole is at the bottom, which is the leading pole as we move through. That's all I can take away from it, because they charge up, and I can show you. I showed you the charging. I'll show you again. But the same thing happens with the green. We caught the green in a half spin, where it was turning, because this is all one picture of the same particle, because it's moving so fast you get them all in one big line. But this is the one with the green in an actual spin. Now look at this carefully. Green is the same as red. They're all the same particle. I believe this is, you see how glowy that is compared to that? I think it's coming through, and then it just got so glowed up that it's going to spin. And that'll go behind, this will come in the front, and this one now is the one that absorbs all the energy. So it's literally a pole shift. In my mind, that's all I can take away from that. But isn't that cool? Just for one last time, that's the particle. This one's the red one. But now, remember I showed you how the green one started glowing and was flipping? That's what's happening here. Now, this is going to glow and flip. And that's just the state of affairs as it moves through the air. Every time it bashes into any of these little glowy particles there, they charge up. That's what's charging that up. This one can't charge up because this is blocking its path. And we got them going through the same venturi at the same time. You can see the difference in the energy values. The red is way less energetic than the green. However, we saw that they are exact same particle. That's light. Okay, it's kind of hard to believe, but light is not understood. I showed you it's a particle, and I showed you the green and the red, and we've also seen the blue. The blue is just kind of too fast to really observe closely like the red or the green. Now, they say light behaves mainly like a wave, but it can also be considered to be tiny packages of energy called photons. We've seen them. Photons carry a fixed amount of energy but have no mass. That is not correct. The photons have a mass, and it's dark energy, the dark mass. It's the black part. The white, I agree, has no mass virtually at all. And that's apparently all they've ever seen. They don't realize the black is attached to it when it's coming through the air. And because you shine light on something, you can push something with light, so it obviously has mass. The energy of a photon depends on its wavelength. Longer, and we know this, the longer the wavelength, the less energy, the shorter, the more energy. So red is less, blue and green is more. Now, until 1900, scientists only understood electromagnetic radiation to be made of waves. They've always said, oh, it's just a wave, and it just propagates a wave. Then Max Planck and others studying photoelectric effect found certain types of metals and other materials will eject electrons when light shines on them. Right? They bash off and they shoot off electrons. They expected that the number of electrons ejected, now this is important, from the metal would increase with the intensity of brightness of the light directed towards the metal. And it does. So don't be confused. It does. However, they found also, they should say, or they all found also, but instead was that the wavelength of the light was what affected the number of electrons ejected. Yes, the wavelength, the more powerful, like you saw the green really makes them flow like crazy. The red, not so much. The blue is even more. However, if you turned up the green higher and higher and higher, you get more and more electrons. So don't think that you can only get the same amount of electrons no matter how high you turn up the light. If it's the same frequency, you're just going to get more and more of those same frequency electrons. And this is what it is right here. The frequency stays the same, but you get more electrons when you flood more light in. All right, see, they're showing green. You get this certain, red and the green and the blue. And I could show you all, well, I will show you. And it goes more energetic wavelengths, such as blue and ultraviolet, cause more electrons to be ejected than red or infrared. They also found that increasing the intensity of the light increased the number of electrons. Exactly. Before they made it sound just not correct. But it didn't change their speed. It made more of them come out because you put more flushing in, but they didn't change their speed. They weren't going faster coming out because you pushed more in. Now, Planck realized that the energy of the electromagnetic radiation was proportional to its frequency, but admitted that he didn't understand why this was the case, and he said it was lucky guesswork. There's a lot of guesswork in this, a lot of lucky guesswork. And if you get real lucky, you get to split particles, which we did. We got real lucky. Einstein was the first to explain what was happening. He theorized the electromagnetic energy comes in little packets. I agree, they're little photons. We now call photons. The light behaves as a wave because it has a magnetic field around it, and as a particle, depending on the circumstances and the effect being observed. Now, I don't think he fully understands that there's some magnetic particles in the center, and they are dipoles. They're not just electrons. That's the key. They thought an electron was just a negative particle. It's not. It's a dipole. And so is the nucleus of every atom. They're dipoles. They're just like a bazillion little tiny electrons together, just like that. But that's a dipole. It has positives and negatives. It's not just one big positive. And so are the electrons that float around the outside. They're positives and negatives as well. And the negative wants to get into the dark matter that is in the center of that nucleus. But it can't get in because there's enough electrons coating the nucleus. It says, no, you stay away, don't come in here. We have just the number we want to coat this dark energy. You stay out. However, if there's an extra electron or not an extra electron, it will want to find somebody to bond with. That's when you get into a bonding situation. Neutral atoms, they don't bond with anything. Anyway, that's a whole other issue. But anyway, Einstein won the 1921 Nobel Prize for his services to theoretical physics, especially his discovery of the law of photoelectric effects. Well, I think we discovered some pretty interesting photoelectric effects our own selves. Okay, my friends, this is just a very quick question for any lawyers that are out there. What is a fiduciary? A fiduciary is a person or organization that acts on behalf of another person or persons, putting their client's interest ahead of their own with a duty to preserve good faith and trust. All right, you trust your fiduciary to take good care of you and to make sure that you're the most important thing because you're paying them. So you expect to get everything that you would expect from a good fiduciary, which in the case of education, It means to be open-minded. Now, being a fiduciary requires being bound both legally and ethically to act in the other's best interest, which would be the students for professors in universities, which would be to teach them the truth. So, and it says here, a fiduciary may be responsible for the general well-being of another, as a guardian would be. Often the task involves finances. That's what you go to school for, is to try to make more money to make a better living for yourself. And you're putting yourself in financial jeopardy when you go and take your loans out for this. You better get what you're paying for. And it's managing other people's assets. You know, money managers, financial. So we have to add universities and professors to this, because they are one of the most serious fiduciaries of all, because you have no authority whatsoever to even speak up against them, because if you protest what they're trying to tell you to say to be intelligent, they will take your money and fail you anyway. And if you say, well, I have all the evidence, they won't look at it. Or if they don't look at it, they're obviously a fiduciary failure. And what the way they handle that is they say, we have peer review and nobody will look at it, so you're not going to be peer reviewed. So this is fiduciary failure from the academic society. So I feel very, very bad for these students that have debt. And they're going to have to be retrained. Somebody's going to I'm just going to do it on the internet, a little flickies here and there. But somebody's going to have to retrain them all. They're going to have to forget what they learned. And that is hard. That's harder than relearning.